Good morning, everybody. Today is Monday, February 26th. Big day today. We don't have a whole lot of time because it's a Monday, so we don't have all of our class period. We have shortened class days on Mondays, but I just wanted to make sure that if you are missing today because you're absent, it is really, really important that you come see me as soon as you get back and you schedule a time to come see me during 8th period guided study. We're running a lab today. Actually, there are 2 labs. And so I want you to be able to reproduce those labs before your end of the unit test on Thursday. Today, you'll need your Chapter 3 notes. We read the article Liquid Oxygen on Friday. And so you'll need to pull that out so that you can take a look at your annotations. And then you can try and do these at home. If you don't have the materials, though, you'll have to do these labs with me. If you can do them at home, you'll need a pen and a pencil. You'll also need 2 pennies. You'll need some rubbing alcohol, water, and some cooking oil. And I'll talk more about that a little bit later. Okay, so we're going to just go ahead and jump in. Remember, we're investigating this question, why doesn't an energy transfer always result in phase change? If you remember, last Friday we had a SIM investigation, and we learned that a substance needs a certain amount of energy transferred in or out before a phase change will occur. We learned that actually it takes more energy being transferred in to cause a phase change than it does energy being transferred out. And we came to learn that the reason why is because the molecules want to come together. And when energy is transferred in, kinetic energy increases, freedom of movement increases, and that causes the molecular attraction to, well, basically the freedom of movement overcomes molecular attraction. And then there's a phase change from a solid to a liquid or a liquid to a gas. Now, if we just want to bring some energy out, a phase change will occur much faster because those molecules have molecular attraction. We're going to do a couple labs today just to kind of give you a hands-on example that you can see with your eyes of what I mean by molecular attraction, okay? So you're going to observe drops of liquid water and compare them to drops of liquid isopropanol. It's basically rubbing alcohol. And I want you to notice whether either liquid evaporates, okay? So in class, the kids had their trays. They had these little eyedropper bottle full of water, and it's just regular water from out by the drinking fountain, and then the rubbing alcohol. So if you at home have rubbing alcohol and you've got an eyedropper, you can do this. If you don't, just listen to me explain it to you, and then you'll come in and do this on your own sometime. You've got to do it, schedule some time with me as soon as you get back. What we're looking for is to see whether the same energy transfer will cause them to evaporate. If we have the same amount of energy going in, will they both evaporate? All right, so we just kind of went through the safety guidelines for science investigations. This one, because we are using rubbing alcohol, I had the kids use their goggles just in case. I don't want them to get rubbing alcohol in their eyes. Also, remember, you're not smelling anything, so please, if you do use rubbing alcohol, don't just put it right up to your nose and smell it. That's really hard on your nasal passages. And then if there's any spills or anything, make sure that if you're doing this at home, that a parent knows you're doing it. And if there are any spills, you get those taken care of right away. Rubbing alcohol is flammable, so you do not want to use this by an open flame or by the stove or by, like if you've got a candle going. Don't be very, very careful. Okay, so you're going to take a paper towel. You're going to write the word water and write the word isopropanol. And you're going to put 2 drops of liquid water below the water label and 2 drops of isopropanol below that label. And then after you draw the water, or after you drop the water, you're going to take a pencil or a pen. You're going to draw a circle around each drop so that you have an indication of where they started. And then you're just going to start recording. We're going to try and run this for about 5 minutes. And then I had the kids go back and check to see what had happened. Now, in between that time, we're going to do another experiment. I want to test the molecular attraction of 2 different liquids, water and oil. So I'm just using regular cooking oil. It'd be kind of cool if you could do another experiment if you wanted to use like vegetable oil versus olive oil versus like avocado oil, or if you've got any other kind of liquid cooking oil. It would be kind of interesting to see how those differ. But what I want you to do is I want you to drop like little eyedropper full of water and the oil on those pennies, and we're just going to see if they're the same. So the directions are to put 2 pennies on 2 different paper towels, and in class the kids worked with their table partner. So partner A's job was to count how many drops of water he or she could fit on that penny without it spilling over. And then partner B counted how many drops of oil they could put on without it spilling over. And we're trying to see, are they the same? And which one do you think was more if they're not the same, and why? So when we're finished with that, then in your notes, I want you to answer the question, do they have the same surface tension? Remember, surface tension, I should have had a picture of that. Surface tension is when we were in your notes, you've got a picture of molecular attraction, where there are little dots indicating that they were the molecules, and then the arrows pointing in all directions, because those molecules want to come together. They want to go towards all the other molecules. And so the surface tension is how those molecules are attracted just at the surface. They're much stronger, and they're not attracted to anything above them. They're only attracted to those below and side to side. And so it's what causes liquids to kind of beat up. And so I just want you to make a comparison in your notes. Draw a picture of what you did. Make some notes and talk about surface tension. And when you explain whether or not they do have the same surface tension, I want you to use the words molecular attraction in your explanation. In other words, if they have the same molecular attraction, then you'll have the same number, or pretty close to the same number of drops for each one. But if one has more or one has less, I want you to make a note of that. Now, by this time, we were finished in class with the isopropanol and the alcohol and the water. And again, I directed the kids to go back to their notes and just make draw a picture real quick. What did you do? And then answer the question, did they evaporate at the same time? Did they both evaporate? If they didn't, why not? If they did, why? If one evaporated faster than the other, why? And again, I want them to use the words molecular attraction in the explanation. Think about that. Molecular attraction means that they don't want to let go of each other. They want to stay in that close state. So, go ahead and pause the video and write that down if you're able to do these experiments at home. And if not, then you can do them in class with me later. Okay, so now let's jump back to the second read of liquid oxygen. Again, we didn't have a whole lot of time in class, and so this was just kind of at the very end. We wanted to talk about why different substances need different amounts of energy to change phase, because you're going to notice that water and the rubbing alcohol did not evaporate at the same rate, and the surface tension between the water and the oil was different because they're different substances, and they need different amounts of energy to change phase. So the rubbing alcohol evaporated very quickly, but the liquid water did not. I want you to reread your second and third paragraphs and get some evidence that answers the investigation question. And then come back. So the investigation question, remember, was why don't they? Why doesn't, let me go back to it really fast. Sorry. Why doesn't an energy transfer always result in a phase change? Just because we add a little bit of energy doesn't mean that there's always a phase change. It won't always go from a solid to a liquid or a liquid to a gas. And just because I remove a little bit of energy does not mean it's going to go from a gas to a liquid or a liquid to a solid. How come? Those paragraphs in your article are really going to help you answer that question. And if you're noticing, by the way, I'm really backing off. I'm not telling you what you need to put in your notes word for word. I'm just directing you to do it. And so in your notes, you're going to answer the question with the article, liquid oxygen. Talk to me about why we can add or remove energy and not have a phase change. Okay, so there's a term, molecular attractions, at the top of your notes on, I think it's page 4. Definition is a pull between two molecules that is always the same for a substance. So the molecular attraction of water is always the same. Molecular attraction of iron or gold is always the same. Molecular attraction of carbon dioxide is always the same. So in the article, it showed this diagram, and I wanted to pull this up real quick just to show everybody and just kind of make sure that check your answer against what I'm going to say. And if that's not what you have, you need to revise. So substance A and substance B are two very different substances, okay? I can tell just by looking at these that they have weaker attraction. The dots are smaller in the substance A. Molecules in substance B have much stronger attraction. And so if you can see that strong attraction is pulling those molecules in substance B closer together. And the molecules in substance A are able to increase freedom of movement because they're not being pulled together. Okay? We're going to continue learning a little bit more about this on, not learning, but we're going to review on Wednesday, and I've got a couple other things in this sim I'm going to have you do if you're not quite understanding this. All right, couple key concepts. Key concept number 9, whether or not a phase change occurs is determined by the kinetic energy and molecular attraction of the molecules. Now, this is way shorter maybe than what you're used to studying. And if you want to cut it down a little bit, please do. I don't want you to get confused and have a hard time remembering these for your test tomorrow. Whether or not a phase change occurs is determined by two things: the kinetic energy and the molecular attraction, because they're inversely proportionate. If kinetic energy increases enough to overcome molecular attraction, there will be a phase change. However, if the molecular attraction is too great and that the kinetic energy cannot overcome molecular attraction, then there will not be a phase change. Even if there's a little bit of kinetic energy going in, if there's a little increase of kinetic energy, if it's not enough to overcome the molecular attraction, there's no phase change. Okay? That's why the butter and the oil in that video that we watched several days ago, that's why the butter and the oil were the same temperature, same kinetic energy, 21 degrees Celsius. But the butter did not change phase because it needed more kinetic energy to overcome molecular attraction. All right, last key concept. The molecular attraction of a substance never changes. Butter will have the same molecular attraction always and forever. And the same with water and air and carbon dioxide and gold, all of them. The molecular attraction of a substance never changes. Okay, that's the end of the lesson for today. Hope to see you tomorrow.